Today in this video I am going to discuss about the magnetic force on a moving charged particle. Well, to understand it, first we consider a three-dimensional reference frame. Okay, suppose this is x-axis, this is y-axis, and this is z-axis. Now we consider a charged particle here. It may be positive charged particle or negative charged particle. We consider it positive charged particle and the amount of charge is q. Now we consider this charged particle is moving along x-axis with velocity v. Next we consider the external magnetic field is applied along the positive z-axis. Okay, whenever the external magnetic field is applied on the moving charged particle, then the external field will apply a force, a magnetic force on the charge. The equation of this force will be F equals to Q V cross B. Okay, now the magnitude of this force will be F equals to Q V sine theta. Okay, from the above equation we get if the theta is 0 degree, that is if the applied magnetic force is along the motion of the charge, then the magnetic force will be minimum and it will be 0. Next, if the angle is 90 degree, then the force will be maximum and it will be QVV. It implies that whenever we applied magnetic field perpendicular with the motion of the charged particle, then we will get the maximum magnetic force, and that is QVV. Now the direction of magnetic force. How we can determine the direction of magnetic force? We can determine the direction of magnetic force by using right hand screw law or Fleming right hand rule. Here the force is F equals to Q V cross B. Now if we rotate a right hand screw from V to B, that is V is along x-axis and B is along z-axis. Now if we rotate a right hand screw from V to B, then it will be clockwise. So the direction of force will be downward. We know from right hand screw law that if the screw rotates clockwise, then its direction is downward. So here the direction of magnetic force will be downward. Again, we can calculate the direction of magnetic force by using Fleming right hand rule like this. Here the first finger will show the direction of motion of charged particle, the middle finger will be along the direction of applied magnetic field, then the thumb will show the direction of magnetic force. So here I am putting my first finger along the velocity of charged particle, then the middle finger along the applied magnetic field, then the thumb will be the direction of magnetic force. So here the magnetic force will be downward. Hope you have understood it. Next, if we apply the magnetic force along the negative z-axis, then the direction will be from V to B, so it is anti-clockwise. According to right hand screw law, the direction will be here upward. Okay, and according to Fleming right hand rule, the direction will be here. The first finger have to taken along the velocity, then the middle along the applied magnetic field, and the thumb will be the direction of magnetic force. So here the thumb is vertically upward, so the magnetic force will be vertically upward. I hope you have able to understand how to get the direction of magnetic field by using right hand Fleming's law or right hand screw law. Now I am going to discuss about the nature of motion of a charged moving particle whenever it is kept in an external magnetic field. Okay, now we consider a magnetic field is applied towards inside of this board perpendicularly, and we can represent it by cross. Okay, this cross implies the magnetic field is inside the whiteboard perpendicularly. Okay, now here we consider a charged particle. It is moving along horizontally with velocity v, and its magnetic force is vertically upward. Then the particle will move along the resultant of force and velocity. Suppose it moves along this path and reach at this point. Here the direction of velocity will be along the tangent, and the applied force will be perpendicular Fm. Okay, next this particle will move along the resultant path and it reach here, and here the magnetic force is here, and the velocity will be perpendicular with the magnetic force. So it will again move along the resultant path and reach here. The magnetic force is along this direction, and the velocity will be perpendicular with the force. So here it is clear that the motion of this charged particle will be circular. Okay, and here the magnetic force will act like a centripetal force. Okay, so we got here that if we keep a charged moving particle in a magnetic field, then it will rotate in a circular path. Okay, and in this case the magnetic force always will act like a centripetal force. So from it we get some mathematical quantities like as the radius of this circular path. So first the radius, in this case the centripetal force must be equals to the magnetic force. That's why the particle able to rotate in a circular path. Next we know the centripetal force is mv square by r, and the magnetic force here is qvb, because here sine 90 degree, that angle is 90 degree here, Okay, next we get from it mb by r equals to qb. So the radius of circular path will be mv qb, or we can write mb is the momentum, so it can denote by p qv. So this is the equation of radius of this circular path. Next we can calculate the time period from it. Time period, we know time period is equals to the distance traveled by the particle. If this particle complete a full rotation, then we get 2 pi r and its velocity is v. Now putting the value r, we get the time period is 2 pi, here r is mv divided by qbv. Next we get t equals to 2 pi m divided by qb. This is the time period of this moving particle. Next we can calculate the frequency from it. We know the frequency is inverse of time period, so here we get qv divided by 2 pi m. This is the frequency. Next, angular velocity or angular frequency can also obtain from the above equation. We know omega equals to 2 pi f, so putting the value we get 2 pi f is qb 2 pi m. Finally we get omega equals to qb by m. This is the equation of angular velocity. Hope you have able to understand it. Now I am going to discuss about the motion, the nature of motion of a charged particle when it moves, making an angle with the magnetic field. Well, here we consider the magnetic field is along z-axis and a charged particle is moving, making angle theta with the magnetic field with velocity v. As this velocity is obliquely here, that's why it has two components. Along x-axis the component will be v cos theta, and along y-axis the component of velocity will be v sin theta. Here v cos theta will help to move the particle along the x-axis, and v sin theta will help to rotate in a circular path of this charged particle. As a result, the motion of the charged particle will be like this, and it is called helix. Okay, the distance traveled by a complete rotation is called pitch of helix.
The video and its content is subjected to copyright. Convention of this video elsewhere is a punishable offense. Any redistribution or reproduction of part or all of the contents in any form is prohibited. You may not issue or commercially exploit the content, nor you may transmit, duplicate, publicly display, or make derivatives of this video. The video is protected by intellectual property claims to stimulate and ensure originality. All rights reserved by Adamjing Cantonment College.